So this is a common collector or emitter follower transistor circuit. And the values in the circuit are given right here in the words of the problem. So we're going to just start with part A. So we're going to label the emitter, collector, and the base of our transistor. So this is our collector, this is our base, and this is our emitter. What kind of transistor is the circuit? Well, the arrow points out of the transistor, so we know that it's an NPN. And it says on the circuit label where on the circuit figure label where the output voltage is measured. So this is an emitter follower, so we know that the output is measured on the emitter. And now we're going to calculate the values necessary to draw the load line, and then we're going to add the load line to the graph, and the graph is down here on the second page. We'll do that. I'll show you that once we do our calculations. And it says draw the model that goes with each calculation. So the two models that we're doing is we're going to look at just the collector to the emitter side, and we're going to do the cutoff mode, which looks like this is our C, this is our E with our transistor being represented by an open, so this is cutoff. And then we're going to have saturation. In the saturation we have this is our VCC, this is our VCC, this is C, and then we just have a wire connecting C and E. We have our resistor. And so to do the calculation here, we know that the VC here is equal to 15 volts. And that's because the current can't flow, so there's no voltage drop here. So C, the voltage at C has to be the same as the source voltage, and so that's 15 volts. And then at E, since there's no voltage drop here, the value at E has to be, it's connected to ground, so it can't be connected, it's not connected to C, so it's got to be 0 volts. So I've got VE is equal to 0 volts. So that means my VCE and cutoff is equal to VC minus VE. And so that's equal to 15 volts minus 0 volts, or 15 volts. And now in saturation, my VC here is equal to, this is 15 volts. VC is connected to VCC, so that means this is going to be my VE is 15 volts, or sorry, VC is 15 volts. And now E is also connected to C, which is connected to VCC. So this VE is also equal to 15 volts. So now VCE is equal to 15 volts minus 15 volts, or 0 volts. Now here current is 0, so I know in the cutoff my IC is equal to 0 amps. But what about for saturation? So for saturation, what I'm going to do is I'm going to just look at this RE value to calculate my max current that can go through here. So I want to calculate IC max, and that's going to equal my VCC over my RE, and that's equal to 15 volts divided by, now RE is equal to 3.75 K. So 3.75 kilo ohms. So this is the maximum value that I can, of current that I can create from this source, right? Because of the limitation of this resistor. So this resistor limits my current when I put a wire between C and E. That's the maximum current I can draw with this transistor circuit. And so my IC max is equal to 4 milliamps. I can undo that. Okay, so we can go down on the load line, or on the graph then, on the next page. And here's our characteristic curves, right? So each of these, it represents the condition where the transistor can operate for different values of IB. And these different values of IB, or my base current, will allow for different values of collector current, right? And so we have a max here. Let's see if I can do this as a line. This might be easier to do than me trying to draw it. So can I drag a line? Oops, not yet. There we go. Can I drag this line? So I've got 15 volts and 4 milliamps. So that looks about right. So I added this is my maximum value, right? So my IC max is 4 milliamps, and that goes along with my VCE of 0 that I calculated here. So my VCE for saturation is 0, and my current max is 4 milliamps. And in cutoff, my current is 0, but my VCE is 15 volts. So that's where they match up. So this is the case where I'm in saturation. So that means I have no VCE because I have that wire between C and E. And I calculate my maximum current is 4 milliamps. Notice that this is 4 times 10 to the minus 3 amps. So that's why I'm saying it's 4 milliamps. And in this case, this is the case where my current is 0. This is cutoff, and cutoff, we have no current flowing, so that's 0, and then my VCE is 15. And so let's go to the next question. All right, so we drew the models. We drew these pictures. Those are the models to go with each calculation. We did our calculations, including the equations, and then we plugged in our numbers. So you need all of this in order to get full credit on this problem. Okay, next part is we need to calculate the voltages. So VB, VC, VE, VCE, and then the currents, IB, IC, and IE. And in order to get full credit, we must provide the equation, plug in the values, and include a final answer. So let's start with VB. So I'm going to just quickly draw the circuit again here. Got my biasing resistors there on my base. And this is 3.75. Okay. And my, so this goes here. And this is my R1, and this is my R2. And these are equal to 34.5. Okay. And this one is equal to 40.5K. Okay, so the first thing I'm going to do is calculate my VB. And so I can do that because I know that this is a voltage divider. So this is my 15 volts, or my VCC. So what I need to do is find the voltage for my voltage divider at this point, and this will be my voltage at the base of the transistor. So how do I do that? Well, for my voltage divider, the equation is VCC times R2 over R1 plus R2. So plugging in, I get 15 volts times 40.5K over 75K. When I add these two together, R1 and R2, that's equal to 70K, or 74, or 74.5, 75K. So that's right. So my VB is equal to 8.1 volts. So I've got 1 down. My V, let's do my VE next. So VE is equal to, so VE is right here. And remember, for this transistor, the voltage drops by the amount of voltage for a diode. So we assume there's a diode, or the model, there's a diode in between the base and the emitter. And so this voltage here is 8.1 volts, and then we subtract 0.7. So we have VE is equal to VB minus 0.7 volts, and that's equal to 7.7 4 volts. So I've got my VE. VC is pretty easy, right? Because there's no voltage drop since, so this is my C, right? So I know my VC, there's no voltage drop, so it's just got to be, it's connected to 15 volts. So my VC is equal to 15 volts. I got VC. So what about my VCE? So VCE is equal to VC minus VE. And so that's equal to 15 volts minus 8.1 volts. And so that's equal to 7 point, no, sorry about that. My VCE is equal to VC minus VE, which is equal to 15 volts minus 7.4 volts. And so then VCE is equal to 7.6 volts. So I got that one. Now I need IB. So what I can do is I know that there's 8.1 volts here, and so that I know there's 7.4 volts right here on the emitter. So what I'm going to do is I'm going to say I have 7.4 volts to drop across the emitter resistor, 3.75K. So my IB is going to be VE divided by RE, and that's equal to 7.4 volts divided by 3.75K. So IB is equal to 1, or sorry, this is not IB, this is IE. Let me see if I can use my eraser. So when I'm doing my calculation here, when I'm saying I have 7.4 volts left on the emitter, and that's got to be dropped across my emitter resistor. So I have IE, the current through the emitter, is equal to VE over RE, and so this is equal to 1.97 milliamps. So I have my IE, so now I can calculate my IB because my IB, well, let's do this first. Let's erase this. We'll use the fact that my emitter current is equal to my base current plus my collector current. And I also know my collector current, so IC is equal to beta times IB. So I'm going to plug this in for this. So that means my IE is equal to IB plus beta IB. And that's equal to beta times, no, that's equal to IB times 1 plus beta. So we can solve for IB now. So that's IE. So that we can solve for IB because we know that IB is equal to IE over 1 plus beta. And that's, we know from the problem, we're told, so let me go back another page, that beta, where is it? Beta is equal to 100. So we're going to use beta is equal to 100. So my IB equals 1.97 milliamps divided by 1 plus beta, so 1 plus 100 is 101. And so for that, therefore IB is equal to 19.5 microamps. All right, so now I have IB, I have IE, I just need IC. So my IC is equal to beta times IB So IC is equal to 100, because beta is 100, times 19.5 microamps. And so therefore IC is equal to 1.95 milliamps. And that's a really good thing to remember, that your IC and your IE should be really similar, right? So 1.97, IE should always be a little bigger, or IE should always be a little bigger than my IC. So remember that in the transistor, I have current going from the base through the emitter, right? And I have current going from the collector through the emitter. So I need to add those together at this point. And so it makes sense that my IC and my IE are similar because IB is so small. Okay, so I think we've calculated, we've got IB, we've got IC, and we've got IE. Let's see what's next. Okay, so this is my graph. And so where on the load line is this circuit operating? Show it on your graph and explain your answer from your calculations. If I look back at my load line, I know that my, if I look up here, I know my base current was 19.5 microamps. So that's really close to 2. This is right here is 20 microamps. 2 times 10 to the minus 5 is 20 times 10 to the minus 6. So I know it's going to operate on this orange line. And so that's here. Oops. Pen back. So I'm operating right around here. And so you might think, like, what about the quiescent point? Right, so the quiescent point, we would be operating where the VCE is for DC operation. So if I go back over here, what we found was my VCE is equal to 7.6 volts, right? So that means that I've got this, like in my model, that I have kind of a resistor in between my collector and my emitter, and that's using up 7.6 volts. So I don't have the full current going through that could go through, and that's why it's an amplifier. It's now I can control how much current goes through. So 7.6 on here, that would be right around here. Right, so right around there would be my quiescent point. So I'm not exactly at my quiescent point, but I'm pretty close. So that means I'm going to have a lot of ability to have swing voltage for my signal to be able to get it through. So my input signal should have no problem getting through there. Okay, so what is the voltage gain of my circuit? Well, remember that this is an emitter follower. And so an emitter follower, my voltage output is right here. That's my V out. And remember that my input signal was right here, and this was a time varying signal, and it was 1.5 volts peak to peak. Right? So the 0.7 drop for the diode was taken care of by my DC voltages, by my voltage divider here. And so my voltage gain is just equal to 1 because my input signal and this signal is going to ride on top of my 8.1 volts. So I'm going to have my input signal is going to look like a sine wave around 8.1 volts. And over here, I'm going to have the same sine wave, but now it's just going to be at 7.6 volts. But I haven't lost any of the 1.5 volts input signal. So I have a gain of 1. So so here I'm going to say my voltage gain, AV, is equal to 1. Let's see if I can make that look a little better. And so show on your graph and explain your answer from your calculations. So you heard my explanations about where it's operating. And we looked at the calculations and we looked at where our quiescent point would be, and that's where we would ignore the AC signal and just look at the DC signal, and we found it to be similar. We also want to write down what our VCE is. and that's equal to 7.6 volts. And our current, so our IC, is equal to 1.95 milliamps. So we can just double check that looking at the graph here. We're at right around, so maybe I'm not quite right, but right around 2 milliamps. So that looks about right. And remember, this isn't quite at 1.95. It'd be a little bit lower, so maybe it would be a little lower over here. But it looks about right. And then in the space below, draw the input signal and output signal on two graphs. Label the horizontal and vertical axes. Okay, so what that means is we're going to draw our input signal. So our input signal, I'm going to really draw actually three graphs because our input signal, our AC input signal, this is volts and this is time. And so we have something that looks like this. That's our AC input signal. And so this is 1.5 volts. And our period would be 1 over the frequency. So what about our DC offset, or DC biased? Let's call it our DC biased input signal. Looks like this. So this is going to be 8.1 volts. And I have this is what my signal looks like, right? It wiggles around 8.1 volts. This is T, right? This is my voltage. So this right here is 8.1 plus 1.5, so 9.6 volts, right? And here is going to be 8.1 minus 1.5. And so what does our output signal look like? So this is our output signal. Looks like, now this time it's around 7.4 volts. Voltage, time, draw that. And now we've got same signal, right? That's why the voltage gain is 1, because our AC signal didn't change at all, right? It's just moved up or down. And so the peak is going to be 1.5 plus 7.4 is 8.9 volts. And down here it's going to be 7.4 minus 1.5. So I think we've answered all the questions in the problem, and this is what you would expect to see for one of the questions for the quiz on Tuesday.